Good morning, all of you. Today we are going to learn imperfections in solids. We know that crystalline substances are of long range order, means regular and periodically repeating pattern is seen for long distances. Although the crystalline substances are of long range order, yet the crystals are not perfect. Some have defect in them. Some have defect in them means defect comes due to the fast cooling. Normally, a solid is made by cooling its molten form. When the molten form is cooled very fast, then defects occur. Perfect crystalline substance is formed when the cooling takes place in a very slow rate. A unit cell is made or formed when the cooling is taken place in a very slow rate. Fast cooling means there will be defects, but we can make use of this defects for its conductivity and all. So in a way defect is a blessing also. So let's see what all types of defects are present in crystals. There are point defects, means from the ideal arrangement, irregularities from the ideal arrangement around a point, irregularities from the ideal arrangement around a point is called point defect. Irregularities from the ideal arrangement in a line is called line defect. Among these two defects, in your syllabus, you have to learn point defects. Line defects you will be studying in higher grades. So, from irregularities, from the ideal arrangement, if the irregularities come around a point, irregularities from the ideal arrangement around a point is called point defect. There are three types of point defects. Stoichiometric defect means stoichiometric defect, impurity defect, and non-stoichiometric defect. Non-stoichiometric defect. Let's see these defects in detail. Irregularities from the ideal arrangement around a point. Point means for us it is an atom or an ion or generally a particle. That is called point defect. Point defects are classified into three categories. Stoichiometric defect. Stoichiometric. Stoichiometric defects. Impurity defect. Impurity defects and non-stoichiometric defect. Stoichiometric defects, impurity defects, and non-stoichiometric defects. Stoichiometric defects means stoichiometry is maintained. For example, NiO. In this Ni1O1, this is in stoichiometry, or 0.9801. See, no stoichiometry. In this case, for 1O, there should be 1 Ni. But in this case, for 1O, 1 Ni is not there. Here we say non-stoichiometric. Means stoichiometry is lost. So, in stoichiometric defects, for example, like NiO, in stoichiometric defects, when stoichiometry is maintained there, classification is vacancy defect and interstitial defect. Vacancy defect. Vacancy defect and interstitial defect. Interstices means voids. Interstitial defect. Vacancy defect means when some of the lattice sites are vacant, means atoms are gone. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in density of the substance. So I am showing vacancy defect. Atom, 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 atom. Atoms are present in this crystal. When the substance is heated, some of these atoms will go up. So there comes the gap. So I am removing some atom. Here is a gap or here is a vacancy. So when some of the lattice sites are vacant, the crystal is said to have vacancy defect. So what happens to the density? Density decreases. Example is boron nitride. Boron nitride. Density decreases. Now, this is the case of neutral things. If the constant particles are made up of ions, then what happens? In the case of ionic solid, I'm showing an ionic solid. Here, Na plus, Cl minus, 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 Na plus, Cl minus. Next to one positive ion, there should be a negative ion. In the case of ionic crystal, the electrical neutrality is to be maintained, means total number of positive charges should be equal to total number of negative charges. Now here, again, some cations and anions are lost. So I am removing cations and anions. Equal number of cations and anions are lost. Here ions are missing. Density decreases, of course. Electrical neutrality is to be maintained. This vacancy defect is called Schottky defect. This vacancy defect is called Schottky defect. This vacancy defect is called Schottky defect. So, what are the characteristics? Electrical neutrality is to be maintained since it is ionic solid. Density decreases, and this happens in those crystals where the cation and anion size anionic sizes are similar. Ions are missing, stoichiometry is maintained. So vacancy defect, generally in vacancy defect, what all things you can say? Density decreases, ions are missing. In the case of ionic solid, in the case of ionic solid, electrical neutrality is to be maintained. In NaCl, there are 10 to the power 6 Schottky pairs per centimeter cube at room temperature. Means so many cations and anions are missing from the crystal in the case of NaCl. Now, let's move to the interstitial defect. Interstitial, that word comes from interstices. Interstices means gaps. Here, when some of the constant particles, ions, occupy the interstitial sites, so I'm making an interstitial defect, that is now what happens when some of the constant particles occupy the interstitial site. So suppose this is shifted to the interstice. This atom or this particle is shifted to the interstices. Or in addition to these particles, some extra particles are coming. So two things can happen. Two things can happen. Extra particles are getting added in the interstices. I am showing that one extra particle here, one extra particle here, one extra particle here, same black only. So what happens to the crystal? Density increases. Here density increases in this case. In the case of ionic crystal, again electrical neutrality is to be maintained. There, how this interstitial defect occurs. So I'm drawing another diagram for this ionic crystal. So here positive ion, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. Next to one negative, one positive you draw. Negative, positive, negative, positive. In this case, that is, in the case of ionic solid, again electrical neutrality is to be maintained. So, the ion, that is a smaller ion, generally smaller ion, is dislocated from its original site. Suppose this is dislocated. Generally, cations are dislocated because it is of smaller size. So, it will be moving to an interstice, a gap. So the ion is dislocated from its normal site. So I am removing from here. I am removing from here, and that is dislocated. That is positive. I removed, and that is dislocated from its normal site to an interstitial site. Site means this interstitial site means void or gap. It creates a vacancy defect. It creates a vacancy defect here at its original site and an interstitial site at its new location. This is the new location. At original site, it creates a vacancy defect, and at its new site, it creates uh, an interstitial site. In the case of this ionic solid, this interstitial defect is called, we call it as interstitial defect only, though here it is a vacancy defect, we have already given here the name. So here, though it is a vacancy defect here, at the new location, it is an interstitial defect. So we call it as this interstitial defect. So the smaller ion got dislocated. I am dislocating one more, that is from here in this plus. So in its new location, it is an interstitial defect. It's also called dislocation defect. Here, the density, what happens to the density? The density remains the same. It does not change the density of the solid. So we'll write here, density remains the same. Density same. We call this defect as Frankel defect. Density same. This defect is Frankel defect. Frankel defect. So in interstitial defect, in neutral case, this is in neutral case. In the neutral case, the density increases. In the case of ionic means positive and negative ion. Example is ZNS. AGBR shows both Schottky and Frankel defect. So in the interstitial defect, density increases. But in the case of this ionic solid, what happens? Positive charges, generally positive, the smaller one will be shifting to the interstices. So in the new location, it is an interstitial defect. Here the density, in Frankel defect, density remains the same. Next we are moving to impurity defect. Impurity means something from outside is entering into the crystal, which causes some defect in the crystal. Again, I am taking NaCl example. This is Na plus Cl minus, Na plus Cl minus, Na plus Cl minus. So many Na plus and Cl minus are there. Since it is an ionic solid, electrical neutrality is to be maintained. Suppose this molten NaCl, solid NaCl is obtained by the crystallization of molten NaCl. When this molten NaCl is mixed with some SrCl2, so what happens? Sr2 plus ions will occupy, or its Sr2 plus ions will replace some of the Na2 plus ion. Suppose here this Na2 plus and this Na2 plus means Na plus and this Na plus means Na total 2 plus. One Na plus here, one Na plus from here. That means total 2 plus. 2 plus charges are replaced by 1 Sr2 plus. SrCl2 has Sr2 plus. So I am taking out this Na plus and this Na plus. Instead of those two Na plus, to neutralize those two plus charges, Sr2 plus can be added. This process is called doping. So what happens? I am removing that Na2 plus. From here also Na2 plus. Instead, I am putting Sr2 plus here. Sr2 plus. So what happens? Here one vacancy. Electrical neutrality is maintained. Why? Because one Sr2 plus replaces two Na plus, Na plus, Na plus. So doping is done. The process is called doping. With this doping, what happens? Vacancies are created. See, here there is vacancy. Vacancies are created. The same thing happens when AgCl, suppose this is of AgCl, is doped with CdCl2. CdCl2. So Cd means Cd2 plus. So 2 Ag plus, 2 Ag plus, Ag plus, Ag plus. 2 Ag plus will be replaced by 1 Cd2 plus to maintain electrical neutrality. But due to this, means in this process, what happens? Vacancies are created. So creation of these vacancy, that is a defect, we call it as impurity defect. So when CdCl2 is added to AgCl, what happens? Vacancies are created. That will change its electrical conductivity. Its many physical properties will be changed by this process of doping. I told you this NaCl when doped with SrCl2, some of this Na plus ions are replaced by Sr2 plus. See, 2 Na plus are replaced by 1 Sr2 plus. Similarly, these two Na plus can be replaced by 1 Sr2 plus. So, how many Sr2 plus are present? Those many vacancies will be created. If NaCl is doped with 10 to the power 10 to the power minus 3 mole percent of SrCl2. What is the concentration of vacancies, cation vacancies? Means how many you are adding, those many vacancies will be created. See how many Sr2 plus you are adding, those many, how many Sr2 plus are getting added, those many vacancies will be created. When one Sr2 plus is present, then one cation vacancy will be formed. Similarly, how many Sr2 plus you are adding, those many vacancies will be created. So 10 to the power mole 10 to the power minus 3 mole percent means these many Sr2 plus you have added. That is 1 moles 10 to the power minus 3 percent. 1 mole means 6.022 into 10 to the power 23. 6.022 into 10 to the power 23. It's 10 to the power minus 3%. That means this is 10 to the power 10 to the power 2. When it goes here 10 to the power minus 2. So it will be 6.022 into 10 to the power 18. These many vacancies will be created. These many vacancies means how many Sr2 plus you are adding, those many vacancies will be created. Suppose 2 Sr2 plus are present in this crystal, then 2 vacancies will be created. Vacancies will change the physical properties of the crystal. Next is non-stoichiometric defects. Non-stoichiometric defects are classified into metal excess defect, metal excess defect, metal excess defect, and metal deficiency defect. Metal deficiency defect. Metal defect. Metal excess defect due to anionic vacancies, due to anionic vacancies. Another one, metal excess defect due to extra cations, due to extra cations present in the interstitial sites, that is voids in the interstitials. So first one is anionic vacancies. So metal excess defect due to anionic vacancies and metal excess defect due to extra cations present at the interstitial sites. So here anionic vacancies, metal excess defect due to anionic vacancies and metal excess defect due to extra cations present at the interstitial sites. First one, we are going to see anionic vacancies. Anionic vacancies means there will be some anions which are getting lost. How this is happening? Let's see. This Na plus, again example Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus, Cl minus, Na plus, Na plus, Cl minus, Na plus, Cl minus, Cl minus, Na plus, Cl minus, Na plus. So many cations or anions are present. Now, when NaCl is heated in presence of sodium vapor, so around this sodium vapors are there. When NaCl is heated in presence of sodium vapor, some sodium atoms get deposited on the surface. Now, Cl minus from the interior will diffuse to the surface and join with Na plus from there. Na plus means Na is deposited over there to combine with Na means the combination is with Na plus only. So what happens? Na from here will change to Na plus and one electron. So Cl minus will diffuse to the surface and combine with sodium. During this process, what happens? One electron will be generated. So what happens? Na changes to Na plus and one electron. So Cl minus will be combining with this Na plus. So this electron generated here will diffuse to that space, that place. So what happens actually when NaCl is heated in presence of sodium vapor? Sodium atoms get deposited on the surface. Sodium atoms get deposited on the surface. Na gets deposited on the surface means that is in the form of atoms. Cl minus get diffused to the surface and combine with Na atoms means Na atoms change to Na plus ions. So the Cl minus diffuses to the surface. So I am removing the Cl minus from here. Cl minus get diffused to the surface and combine with Na plus over there, and from there electron gets diffused to this. From there electron gets diffused to this, so electron will be coming here, one electron. So ultimately what happens? Ultimately there is metal excess, sodium excess now, because one Cl gone, Cl minus gone, so sodium is Na plus is excess. That's why we are telling metal excess defect due to anionic vacancy. This is an anionic vacancy. Anionic vacancy occupied by electron is called F sender. F sender means color sender. Due to this, crystal gets color. Crystal gets color. So this F sender means far bend sender, means color senders. So what is F sender? Anionic vacancies occupied by electrons are called F senders. Anionic vacancies occupied by electrons are called F senders or far bend sender. So due to this, NaCl becomes yellow. It imparts a yellow color to this NaCl. You must have seen sodium vapor lamp. Sodium vapor lamp. In the sodium vapor lamp, electricity is passed and it is heated. So it is heated in presence of sodium vapor. So we are calling it as sodium vapor lamp. When it is heated in presence of sodium vapor, some of the sodium atoms are deposited on the surface. Cl minus from the interior diffuses to the surface and combine with Na plus there. And the electron generated here diffuses to this anionic site. Anionic site occupied by these electrons are called F senders, which imparts the color to the crystal. So that's about anionic vacancies. Metal excess defect due to anionic vacancies. So this anionic vacancies impart yellow color to NaCl and violet color to KCl and pink color to LiCl. Now let's move to extra cations. Extra cations, for example, ZnO. Zinc O is white at room temperature, but when it is heated, it changes to Zn2 plus. And what happens? Oxygen will be liberated. On heating, oxygen gas will be liberated, plus two electrons will be formed. So what happens here? Oxygen is liberated, means there is gaps. To these gaps, Zn2 plus will be shifted. Zn2 plus, due to its very small size, it can shift to the interstices. Metal, here we call it as metal excess defect due to extra cation present at the interstitial site. Here cation is very small, Zn2 plus is very small, oxygen gas goes up. So the Zn2 plus shifts to this interstices. So metal excess, again metal excess, because anions are escaping. Metal excess defect due to extra cations present at the interstitial site. Now what happens? Due to this presence of electrons, it changes to yellow color. ZnO is white at room temperature, but on heating it changes to yellow color. Yellow color is due to the presence of these electrons. But in this case, the difference is that Zn2 plus being small will be shifting to this interstices. So extra cations present at the interstices. So next is metal deficiency defect. In metal deficiency defect, I am rubbing off these metal excess defects due to anionic vacancies and extra cations present at the center. Now I am drawing for metal deficiency defect. For example, FeO. See, this is non-stoichiometric defect. FeO, that is Fe2 plus O2 minus, 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 O2 minus, Fe2 plus 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 O2 minus, Fe2 plus. FeO, if it is FeO, that is Fe1O1. But here we are telling it is non-stoichiometric. That means, for example, Fe 0.93